Hi, I'm Sang-Jun Han. Today I'm going to talk about single-gate electro-optic beam switching metasurfaces, which is published in arXiv in 2024. Let's go into it. In this work, we focused on developing an electro-optic beam switching metasurface that operates with a single gate voltage, eliminating the need for complex driving circuits while still achieving enhanced performance. By leveraging a genetic algorithm, we optimized the metasurface structure, fabricated the device, and experimentally demonstrated a 57-degree single-gate electro-optic beam switching, achieving improved performance compared to previous studies. Furthermore, through Quasinormal mode analysis, we were able to uncover the physical origin of the beam switching mechanism, providing a deeper understanding of how this metasurface effectively controls light. This work not only enhances the practicality of electro-optic beam switching, but also established a new design framework for next-generation reconfigurable metasurfaces. Beam switching, or beam steering technology, got a lot of attention recently. With this device, we can do many things such as free space optical communication, LiDAR, optical counterpart of the multiplexer in the optical computing, or tunable beam splitter, which is widely used in quantum experiments. However, conventional beam switching devices were quite bulky and commonly utilize a mechanical operation mechanism, so have a limitation with its endurance and heat management. Therefore, recent research has focused on active beam switching devices that can modulate without changing its structure. There have been several conventional approaches to beam control, which with its own advantages and drawbacks. One widely used method, especially by companies like Oster Velodyne, involves using rotating reflective components to steer the beam direction. The biggest advantage of this approach is that it can theoretically achieve a 360-degree field of view. However, it comes with significant downsides. The system tends to be quite large, generates a considerable amount of heat, and suffers from a high power consumption ranging from tens of milliwatts to several watts. To address these issues, researchers have explored MEMS-based beam control using microactuators. This method offers benefits such as compact size and low power consumption. However, it also presents challenges, lower durability, reduced stability, and a limited operation speed of few megahertz, which restricts its applications. If we focus on LiDAR applications, another alternative is flash LiDAR. This approach directs a laser onto a well-designed solid-state diffuser, spreading the laser beam across a broad field of view and capturing target information instantly. Flash LiDAR doesn't involve actual beam steering, but rather beam spreading, allowing for extremely fast data acquisition. However, there are trade-offs. The diffusion process leads to efficiency loss, resulting in higher power consumption. Additionally, compared to some of more advanced methods I'll discuss later, flash LiDAR components remain relatively large, typically on the millimeters scale. To overcome the limitations of conventional beam control methods, researchers have been actively exploring metasurface-based beam switching as a promising alternative. Since passive metasurfaces cannot dynamically change the beam direction, a great deal of research has focused on developing active metasurfaces that integrate various tuning mechanisms for real-time beam control, and several innovative approaches have been proposed. By utilizing materials that change phase with temperature, researchers have demonstrated a method where the beam direction shifts dynamically based on thermal modulation. And another approach involves applying spatially varying voltages to a liquid crystal layer embedded in the metasurfaces. This alters the scattering properties of the meta-atoms, effectively shaping the free-fronts and steering the beam as you need. Some studies have taken it a step further by incorporating mechanical deformation or integrating nano-electromechanical systems with metasurfaces for beam steering. Now let's talk about electro-optic beam control, which offers several advantages over both other active metasurface approaches and conventional beam steering methods. One of the biggest benefits of electro-optic devices is that they can be made extremely small, much more compact than many of the previous mentioned methods. Unlike thermal-based or mechanically deformable metasurfaces, electro-optic tuning does not rely on temperature changes or structural modifications, meaning it produces almost no heat during operation and mechanically stable. Most electro-optic metasurfaces use capacitive carrier injection for modulation. Since the capacitance can be made very small, the power consumption is significantly reduced, and the response time is much faster, allowing for high-speed beam control. And one key consideration with electro-optic tuning is that the refractive index change is typically quite small. To compensate for this, electro-optic metasurfaces commonly rely on strong resonances to enhance light-matter interaction, ensuring effective beam steering even with subtle index modulations. Additionally, like many other metasurface designs, electro-optic metasurfaces often adopt a unicell-based forward design approach, making the design process intuitive and structured. While electro-optic metasurfaces offer many advantages, there are still some key challenges that need to be addressed. I mentioned two common characteristics of electro-optic metasurfaces. They rely on strong light matter interaction, and they are typically designed using a unicell-based forward design approach. However, these features also introduce fundamental limitations that must be overcome. Because electro-optic metasurfaces are designed for strong light matter interaction, they inherently suffer from higher optical losses. Ironically, this can lead to a reduction in optical efficiencies, which are crucial for effective beam steering. Since most electro-optic metasurfaces use a unicell-based forward design, they assume that each meta-atom operates independently. However, in reality, neighboring meta-atoms interact with each other, which can lead to a significant design issue. This becomes particularly problematic when rapid phase changes need to be implemented across space. The strong coupling between adjacent meta-atoms can cause uneven diffraction efficiencies among different orders, leading to undesirable beam shaping effects. And another key challenge in beam switching is the need for complex driving circuits. Many previous designs require spatially varying voltages, making fabrication difficult and limiting device miniaturization. This complexity increases failure risk and hinders integration, highlighting the need for a simpler, more efficient approach. So in this study, we explored a single-gate electro-optic beam switching metasurface. Unlike conventional designs that require spatially varying gate biases, this metasurface enables high-performance active beam switching with just a single gate. This approach simplifies the control mechanism while maintaining excellent efficiency, making it a highly promising solution for practical electro-optic applications. First, I will explain the optimization process of the device structure. For this metasurface design, instead of using the conventional unicell-based forward design approach widely adopted in previous studies, we optimized the entire metasurface. This method allows for performance optimization even when significant interactions exist between adjacent meta-atoms. The design metasurface consists of graphene gold grating placed on a substrate made of gold, silicon nitride, and aluminum oxide. The graphene layer completely fills the gaps between the gold antennas, and a DC gate bias is applied between the bottom gold layer and the top graphene layer. By adjusting this gate bias, the beam is actively switched between the zeroth order and minus first order diffraction modes, achieving dynamic beam switching. To evaluate the beam switching performances, we primarily used absolute efficiency and relative efficiency as a key performance metrics. Absolute efficiency is the ratio of the output beam power at a specific angle to the total incident beam power. In other words, it quantifies how much of the beam power is directed into a desired beam angle. Relative efficiency is defined as a ratio of the absolute efficiency at a specific angle to the total absolute efficiency across all angles. This metric indicates how effectively the beam is switched toward a target angle while minimizing side loads. By leveraging these optimization techniques and performance metrics, we aim to achieve high efficiency single gate beam switching with minimal loss and high efficiencies. Given the large number of tuning parameters involved, a brute force search approach would be highly inefficient for optimization. To handle these multiple variables efficiently and accelerate the optimization process, we employed a genetic algorithm, which is a well-established yet highly powerful optimization technique. In this approach, each optimization parameter described earlier was treated as a gene, and together they form a gene pool. The performance of each gene was evaluated based on figure merit, and through iterative improvements, the gene pool was evolved to maximize this figure merit. To calculate the figure merit of each gene, we used Reticolo, a rigorous coupled wave analysis tool that provides precise simulations of the metasurface's optical response. The figure merit used for optimization was designed to simultaneously maximize both absolute efficiency and relative efficiency. To explain in more detail, we employed a minimax strategy to optimize the performance across two target scenarios. When the graphene Fermi level is at state A, we aim to maximize the absolute efficiency of the minus first order diffraction. When the Fermi level is at state B, we aim to maximize the absolute efficiency of the zeroth order diffraction. Instead of optimizing them separately, we maximize the lower value of the two, ensuring that both states perform well and avoiding cases where one state is highly efficient while the other is underperforming. The same minimax approach was applied to relative efficiency as well, ensuring that beam switching remains highly directional with minimal side loads. The final figure merit was then simply calculated by multiplying the absolute and relative efficiency, providing a compact and effective optimization criterion. And to further enhance performance, we introduced a threshold-based selection strategy. If a gene's performance falls below a predefined threshold, it is strongly penalized or completely eliminated from the gene pool. This step function approach helps prevent poor performing structures from slowing down the optimization process and ensures a faster convergence toward high efficiency designs. So ultimately, the ideal figure merit value is 1, meaning perfect optical efficiency, and we aim for higher figure merit values. And here is the final optimized result. When a 40.49 THz TM incident beam enters the structure at a 45-degree angle, the metasurface successfully switches the reflection order based on the graphene Fermi level. At 0.1 electron volt, the beam is reflected into the minus first order. At 0.45 electron volt, the beam is reflected into the zeroth order. The figure merit rapidly converges within 10 to 20 generations, reaching a value of 0.689, demonstrating efficient optimization. The absolute efficiency for each diffraction order was measured at 0.216, while the relative efficiency reached 0.925, indicating a highly directional and well-balanced beam switching performances. These results confirm that optimized metasurface effectively achieves high efficiency and even efficiency across the target diffraction orders. To ensure the beam switching performance remains robust against potential fabrication errors, we tested the tolerance of the optimized metasurface structure. One major source of errors comes from the E-beam lithography, which introduces slight variations in the gold grating structure during fabrication. To account for this, we assume that each antenna width follows a normal distribution with a standard deviation of 50 nanometer and conducted 1,000 Monte Carlo simulations to statistically analyze the impact of these variations. The results shows that within this fabrication error range, the target frequency may experience a slight shift, but the figure merit remains largely unaffected, with an average value of 0.65, which is very close to the optimized results. The standard deviation was also low, indicating that the structure exhibits high tolerance to fabrication errors. And we also evaluate tolerance to graphene carrier mobility variations. Since precisely controlling graphene mobility during fabrication is quite challenging, we investigated how performance trends across a wide range of mobility values. Encouragingly, even when carrier mobility dropped as low as 150, simply shifting the operating frequency slightly allowed the metasurface to maintain a reasonable high figure merits. Moreover, when graphene mobility increased, the metasurface performance remained highly stable, demonstrating strong resilience to variations in graphene quality. And secondly, this is how we fabricate the device and measure the optical properties. We made our device using this device fabrication processes, including photolithography and E-beam lithography and graphene transfer method and lift-up processes. And here is the fabricated metasurfaces. The electrode lines extended outward to supply the single gate voltage, enabling electro-optic tuning. Upon closer inspection, we can see the metasurface pattern clearly defined. While there are slight deviation in structural parameters due to fabrication errors, the gold antennas and gap structures are well formed and precisely defined, ensuring that the overall functionality remains intact. The beam switching measurement setup was configured as follows. A quantum cascade laser was used to generate mid-infrared light, and the D's beam was then focused using a parabolometer, and tightly focused light was incident on the metasurface at a 45-degree angle. For this experiment, measurements were conducted at a target frequency of 41.17 terahertz, and the reflected beam from the metasurface was measured using a polymeter mounted on the rotation stage, allowing us to record the intensity at different refraction angles. First, measure the electrical characteristics of the metasurfaces. The applied voltage was increased up to -80 volt just before the breakdown threshold. While some leakage current was observed, the voltage cycle remained stable, confirming the reliability of the device operation. We then examined the graphene sheet resistance and identified that the direct point voltage was located at 10 volts. From this, we calculate the Fermi level shift in graphene when sweeping the voltage from 10 volt to -80 volt. The Fermi level varied from 0 electron volt to approximately 0.42 electron volts. Additionally, at the direct point, which is 10 volt, the sheet resistance did not diverge to infinity, but instead remained at a finite value. This is a well-known phenomenon in graphene devices, often attributed to residual charge carriers, which prevent a complete depletion of free carriers even at the charge neutrality point. Our measurements also confirm this effect. The optical measurement results confirm the successful beam switching performance of the metasurface. When applying 10 volt, the strongest absolute efficiency was detected at -12 degrees, corresponding to the -first order diffraction. When applying -80 volt, the highest absolute efficiency was observed at 45 degrees, indicating dominant specular reflection. Additionally, we observed that the side lobes were significantly weaker than the main lobes, demonstrating the metasurface's ability to efficiently direct light with minimal unwanted diffraction. And in the right-hand graph, plotting the optical efficiency as a function of gate bias and diffraction order, we see a clear crossover trend. The efficiency of the -first order starts high at 10 volt, gradually decreases, and crosses over with the 0th order efficiency at -80 volt. The maximum absolute efficiency for each order were measured as 8.4% for the -first order and 7.8% for the 0th order. And looking at relative efficiency, a similar crossover behavior was observed, with peak values of 0.765 for the -first order and 0.836 for the 0th order, confirming strong beam switching performance with high directivity. And these results experimentally demonstrate single-gate electro-optic beam switching at 41.17 THz, achieving a 57-degree beam switching range, validating the effectiveness of our optimized metasurface design. To investigate the limitation of this design platform and explore potential improvements, we conducted additional simulations. In this study, the minimum feature size was 70 nanometer and the graphene carrier mobility was relatively low at 200. However, if graphene mobility were improved and the EBL process were further refined to achieve a minimum feature size of 20 nanometer, we found that the metasurface's performance could be significantly enhanced. With these improvements, the absolute efficiency could be increased to 38.5%, while the relative efficiency could reach 0.976, resulting in a figure merit of 0.84. This represents a major leap in performance, demonstrating the potential of higher resolution fabrication, improved material quality, and improving the efficiency of electro-optic metasurfaces. Additionally, we explored the possibility of 3-level beam switching by extending the graphene Fermi level tuning range up to 1 electron volt. Simulation shows that the single-gate 3-level electro-optic beam switching mechanism can be achieved. This system maintained an absolute efficiency above 14.8%, while ensuring that the relative efficiency remained above 0.85 across all switching states. Finally, we analyzed physically how our metasurface can switch the light with only a single gate bias. We first conducted electromagnetic simulations using RCWA to analyze the metasurface's optical response. The solid lines represent the measured spectral data at 10 volt and -80 volt for the 0th and -1st order diffraction angles, while the dotted lines show the simulated spectra calculated using the experimentally measured structural parameters and corresponding graphene Fermi levels at those voltages. The two sets of data align very well overall. One notable deviation appears in 0th order spectrum at 10 volts, where the measured and simulated results show a slight mismatch. We suspect this arises from either residual charge effects at the charge neutrality point or spectral inhomogeneity in the fabricated gold layer. However, since this discrepancy does not significantly alter the overall physical behavior, we proceeded with further analysis based on the simulation results. Next, we examine the scattered far field distribution at the target frequency as the function of the Griffin Fermi level. The right side figure clearly shows that as the Fermi level changes, the wavefront undergoes a significant modulation. The scattered wavefront remains clean and well-defined, confirming that the beam is switched efficiently and highly directive. Despite the sharp wavefront modulation, the E-field and H-field intensity profiles around the metasurface do not exhibit significant variations. Typically, when such drastic wavefront changes occur in metasurface and the behavior is driven by individual meta-atoms, we would expect to see the localized phase shift across the metasurface, potentially spanning from 0 to pi in certain range. However, in this structure, we do not observe such drastic localized phase responses, suggesting that the beam switching mechanism here does not follow conventional meta-atom driven interaction. This led us to reconsider the traditional unicell-based approach commonly used for metasurface design analysis. Instead, explaining this behavior in terms of individual meta-atoms, we needed to explore an alternative framework that better captures the global metasurface response responsible for the observed beam switching performances. To explain the beam switching behavior of this metasurface, we adopted an alternative approach, identifying the non-local quasi-normal modes present in the system and analyzing how their interactions drive the observed optical responses. This method is based on the assumption that the metasurface response can be decomposed into a combination of quasi-normal modes and a background mode. By doing so, we can isolate how each mode influences the metasurface's optical response and how they collectively enable dynamic beam switching. Since quasi-normal modes exhibit divergence at their resonance frequencies, we can identify their poles in the complex frequency plane by analyzing the system's spectral response. I extended the reflection amplitude spectra into the complex frequency plane for both 0th and -1st order diffraction and for two different Griffin Fermi levels. The resulting plot provides insight into how the metasurface resonance behavior changes with voltage control. The pink and purple lines here indicate the real frequency reflections, which directly correspond to the spectrograph shown earlier. The marked point represents the resonance frequencies of the quasi-normal mode, which is poles. And here's several key observations emerged from this analysis. The quasi-normal mode poles appear at the same locations for both 0th and -1st order diffractions, meaning that the metasurface's beam switching behavior is governed by a shared set of resonances rather than independent diffraction channels. As the Griffin Fermi level increases, the poles shift toward higher frequencies, confirming that the resonance dynamically respond to voltage tuning. The overall shape of the reflection spectra is determined by the interference between these quasi-normal modes and the background response. The dominant mode, quasi-normal mode 1, plays a major role in shaping the spectral response, while quasi-normal mode 2 is located far in the complex plane from the real frequency axis and contributes only a minor effect. So quasi-normal mode 2 has minimal influence on the real frequency response. I incorporated its effect into background responses. And we can decompose the complex reflectivity spectrum along the real frequency axis using the Wright's projection. And here is the complex reflectivity decomposition for both 0th and -1st order diffraction at two different graphene Fermi levels. The key factor governing the beam switching behavior is the interference between quasi-normal mode 1 and the background responses. To visualize this, I plotted the solid line representing the decomposed spectrum of quasi-normal mode 1 and the dotted line representing the background response spectrum, and the red solid line showing the sum of these two components. The circle markers, which represent the RCWA calculated reflectivity for comparison. And as you can see, the red line and the RCWA data closely match with each other, confirming that the decomposition was successfully performed, meaning this method effectively captures the metasurface's behavior. And another crucial factor is the phase difference between quasi-normal mode 1 and background response. So I draw it in the bottom line. Now let's explain why this metasurface enables beam switching. At the CMP in the 0th order, quasi-normal mode 1 and the background mode have similar amplitudes but are out of phase by pi, leading to strong suppression of the 0th order reflection. In contrast, the minus 1st order reflection is suppressed much less, allowing more of the beam to be directed into this minus 1st order diffraction order. As a result, at CMP, the metasurface switched the wavefront toward the minus 1st order. Similarly, at 0.42 electron volt, the metasurface exhibits a different beam switching behavior due to changes in amplitude and phase relationship between quasi-normal mode 1 and the background mode. At this Fermi level, the amplitude difference between quasi-normal mode 1 and background response is similar for both 0th and minus 1st order diffraction, meaning that amplitude alone does not explain the switching behavior. However, when examining the phase difference between these two modes, we can see that for the minus 1st order, the phase difference between these two modes is close to pi, leading to strong destructive interference and suppression. In contrast, the 0th order does not experience this pi phase difference, meaning it is less suppressed and thus dominates the reflected wave. As a result, at 0.42 electron volt, the wavefront switches to the 0th order direction, effectively changing the beam switching angle. Through this analysis, we have successfully explained why the wavefront undergoes a sharp transition as a function of the graphene Fermi level, revealing the underlying quasi-normal mode interference mechanisms that enables this single-gate beam switching. So this is the end of the presentation. If you have any questions, you can contact with these mails. Thank you so much.